Yeah, SO4 is a 2 minus. Yeah.
Good. It's going to be Al2SO4 parentheses 3. That's right.
So that would be aluminum sulfate. And so what we're going to do is we're just going to go down the list.
So we're going to look at percent aluminum first. Well, in order to do that, we need the total mass, so let's first do that. So I have 2 aluminums.
And then let's figure out what the mass for aluminum is. Right here. 26.98.
So that would be 2 times 26.98. Again, I'm going to leave off the units since we have some choice there. Then I'm going to go to sulfur. How many sulfurs do I have? 3 sulfurs. It's going to be 3 times 30. What is sulfur? 32.07. And then how many oxygens do I have? 12 oxygens. It's going to be 12 times 16.00. All right, so let's calculate those
Individually first and then combine them.
So 2 times 26.98, 53.96. 3 times 3207, 96.21. And then 12 times 16, 192. Except, you know, the sig figs here, when I do the 192, it comes out to how many sig figs am I allowed? I'm allowed 4. And so this is going to limit the number of decimal places. Do you see that? Now if I go 4 sig figs here, it only goes to the nearest 10.
But this turned out to be one of the problems with the sig fig rules. One of the problems with the sig fig, what kind of balance did we use? Did we use a 1/10 of a gram balance? Yeah. 1/10 of a gram balance you could probably buy for $10 or something on Amazon, right? If we go to 1/100 of a gram, you know how much 1/100 of a gram balance comes out to? The ones we use in lab are 1/100 of a gram. Do you know how much those cost? $500. If we go to 1,000th of a gram, 1,000th of a gram would be about $1,000. And a 10,000th of a gram, do you know how much that is? No, half of that. $5,000. $5,000. So did we all of a sudden, did we switch balances? Did we all of a sudden, if we followed the sig fig rules properly, we should round this to the nearest 10. Did we all of a sudden go from a $500 balance to a $10 balance? No, and so this is one of those cases where you can take it case by case. If you followed the sig fig rules and just said, okay, I'm only allowed to the nearest 10th, then that's okay. You followed the sig fig rules. But if you want to go and take a step beyond the sig fig rules, we're going to just keep it to the nearest 100. You know, otherwise, why bother buying a $500 balance? So I'm going to keep it 7, and so I'm going to call that 7 significant. 1. It turns out we don't run into that problem if we use something called propagation of errors. It's 18. Right here. 10, 12. Oh, I see. 15, 24. 342.17. Is that what you guys got? Okay. So let's do the percent aluminum. I have 53.96 total aluminum over 342.17 total times 100%. So 53.96 divided by 342.17. 15.769.
15.769% aluminum by mass. Okay.
Then we'll go to percent sulfur. It's going to be 9621 divided by 342.17. So times 100%. .117% sulfur. And we'll go to percent oxygen. 192 by 347 or 342. Sorry, 0.17. 100%. 192 divided by 342. 117. 56.112 oxygen. All right, so this would be the percent composition by element for aluminum sulfate. We could do a check. One way to check it, our answer is all these should add up to what? 100%. So let's just make sure we aren't missing anything or made some calculation error. So I'm going to go 15.769 plus 28.117 plus 56.112. I get 99.998%. I don't get 100%. 99.998%. I must be missing an element. Am I missing something? Is some element missing? No, I mean this is very. I'm only missing 0.002%. 0.02 would be 2,000%. 0.002%. What would you attribute that to? Was there some kind of impurity in there? Maybe there's an impurity in there. No, it's not. There's no impurity because we pure aluminum sulfate. You can't throw anything hidden in there. And so why isn't it adding up to 100%? Yeah, because of round off error. If I didn't round these and I carried all the digits in my calculator, you could do it. It'd add up to 100%. So this is just rounding error. But that's okay. We would round this. We're not allowed 5 sig figs here. We would be allowed, looks like 4. So we'd round it to, well, I mean 2 decimal places. So we'd round it to 100%, 100.00%. So they got 15.77%, 28.11%, 56.12%. Their numbers came out a little bit different than ours, but they got 100%. Did they really get 100%? Well, it does look like it. This looks like it adds up to 100%, which is nice. We didn't. It's not a problem. All right, aluminum chlorate. Let's first figure out what is the formula for aluminum chlorate. Parentheses 3. Wow, that's good. That's good. Aluminum is plus 3. ClO3 minus is, yeah, chlorate. Right? Has a -1 charge, so we'll need 3 of them. Aluminum chlorate is 38.35% chloride. 38.35% chloride. Hey, what's the formula for chloride? Cl 1 minus. I have a problem with this though. You know, the problem I have with this is this. Is there any chloride in chlorate? Is there any chloride in chlorate? Let's say, you know what? You ran out of salt. Say you wanted to put some salt on some French fries. You ran out of salt, but you have some chlorate, sodium chlorate instead. Then you recall, hey, there's chloride in chlorate, so I can use that instead. Would it work? No. No, not even close. I mean, because if you think about chlorate, you know, and in fact, I don't understand where they're getting chloride from, because when I look at chlorate, it's like this. That's ClO3 minus. And if you think of oxygens as 2 minuses, what is chlorine? If oxygen is 2 minus, what is chlorine? Plus 7? So plus 7 minus 6 gives us plus 1. It's got to be plus 5. Well, it's not really like a plus 5 cation, you know, and so sometimes we'll use a Roman numeral there, you know, to indicate that it's not, because, you know, chlorine in the plus 5, do you think it's all that happy being in the plus 5 state? Well, in other words, is chloride happy being in the minus 1 state? You know, yeah, I mean, it's pretty happy. There's lots of sodium chloride all over the place, right? And it seems pretty happy. I mean, just sits there, doesn't really do anything. So that's happy. Except, you know, seasons your French fries. Of course, you don't want to eat something that is not happy. You don't want to eat an unhappy chemical, because unhappy chemicals are going to cause you trouble. But sodium chloride is a chemical that's fairly happy, and it's generally regarded as safe. Have you ever heard that? Generally regarded as safe. Generally regarded as safe doesn't mean you want to eat pounds of it, because if you start eating pounds of it, you're going to be in trouble as well, right? But if you eat small quantities, it should be okay. How about chlorates? Are chlorates generally regarded as safe? What's your suspicion? No. And so this is a big error. You know, there's no chloride in chlorate, not even close, because chloride's happy, chlorate's unhappy. Simple. And so we need to change this. We shouldn't say that aluminum chlorate is 38.35% chloride. It's a typo. This is a typo, obviously, because they should have said aluminum chlorate is 38.35% chlorine. And then it's not a problem, because there are chlorine atoms in chlorate. No big deal. Even though they have a charge, there's still chlorine atoms, you know, with a charge, with no ion. But anyway, it should have said chlorine. This is like the chlorinating solution. Do you know what they use mostly for chlorinating solutions for swimming pools? Do you think they use chlorine for chlorinating solution? You would think so, but a lot of the chlorinating solutions they use, go to like Lowe's and looked at their chlorinating solution. This was the active ingredient. This is called sodium hypochlorite. Sodium hypochlorite, is the chlorine happy in hypochlorite? What do I mean by happy? This is what I mean by happy. Okay, you have this. This is called chloride. Any problem eating this stuff, like in salt? Cause you any stomach upset? Well, there's too much salt, of course, with the sodium ion. How about this? If you ran out of chloride, like sodium chloride, could you substitute chlorine, you know, like green gas, instead? Would that work? No. And so it seems like, oh, this is okay, but this is not as okay. What about this? Is this going to be less happy than this or more happy than this? What's your guess? Let's see, this is ClO minus, which we call, what do we call that? Hypochlorite. Sodium hypochlorite bleach, although the chlorinating solutions for swimming pools are much higher in concentration than the ones you get in the supermarket. They're like anywhere from 10% bleach to 30% bleach versus household bleach. Household bleach is pretty dilute. But anyway, bleach's action has to do with sodium ions, right? Sodium ions cause bleach to whiten clothes and all that other stuff. Is that right? Or bleach's action happens because of hypochlorite. Don't really know? If you don't really know, then you think about sodium ions in the past, your experience with sodium ions. Probably your only experience with sodium ions is from table salt. And so if you ran out of bleach, you run to the kitchen and grab a salt shaker. Will that do the same thing? Just dump a whole bunch of salt into your washing machine? Will it do the same thing? No, and so probably it's not the sodium, it's got to be the hypochlorite on it. And then when we look at this, is it so happy? Well, if oxygen is -2, what does that make chlorine? +1. Is that becoming more happy or less happy with the chlorine? Less happy. And so you'd expect this chlorinating solution to be more powerful than chlorine in water. Perhaps. But we've got to verify that. Well, anyway, we fixed this, and so this means that it's 38.35% by mass or by atom. If it doesn't say, then we're going to assume it's by mass. And so, in other words, let's take a look at the problem here. What mass of aluminum chlorate is needed for as a source of 50.0 milligrams of chlorine? So if we start off with 50.0 milligrams of chlorine, how much aluminum chlorate do we want? And so we're just going to use this. It's going to be 38.35 milligrams of chlorine for every 100 milligrams of aluminum chlorate. The milligrams of chlorine, this pure chlorine cancel, that leaves us with milligrams of aluminum chlorate. Which is, here they do it the way I like it. Here, they write extra digits because we're only allowed how many sig figs? We're allowed 3. And so we show more and then round it. That's the way I like it shown. So 130.3, rounded to 130, so 1.30 square milligrams. So this slide is good. But if you look at the previous one, they automatically round things. Here. Oh, actually, this is good too. This is good. And so, like I said, they must have a different person here because normally they would have just shown 2 there. But they showed extra. I don't need you to show me that many extras. I just like you to show me the drop digits. Oh, this is not good because what did they forget? They forgot to round it. How many sig figs am I allowed in this? So good that they showed me extra digits, but bad they didn't round this because this should be rounded to 1.5 times 10 to the 23rd. This is bad. I don't like this. Why? Yeah, they didn't show me the drop digit here. I want to see the drop digit. What was the drop digit? A 4? Or did they round it up? Maybe it was 6, 8. Maybe it was 6, 6. I don't know. I want to see what it was before rounding. So I didn't like that. Okay, I like this. This is good. We're allowed 3 sig figs. This shows 5 here, so you don't have to show the 7. 130.3. Just show me the 1 extra. And show me what you drop. You drop 3. That's fine. Here's if you drop 3 in this one. All right, and then I don't know what they're doing there. I'm going to skip that. Then we're going to go to this. So these formulas are mass ratios or atom ratios here. Atom ratios. Where do the formulas come from? And so we're going to revisit empirical formulas. Can you remind me what an empirical formula is? Talked about empirical formulas, I think, in the first week. What are empirical formulas? What is it? Oh, yeah, mathematical equations. Half right. Empirical equations are the mathematical equations. Empirical equations are equations that come from empirical equations get turned into laws. The empirical equations do not come from laws. So for example, Charles' law, somebody all of a sudden thought, oh, I have an equation. This equation is an empirical equation, I'm going to convert it into my law, Charles' law. No. Comes from observations. But that's different. This is a different empirical. This empirical refers to something totally different, and they're not even connected. And so an empirical formula and an empirical equation are two totally different things, unfortunately. So an empirical formula refers to what? For example, we talked about this. Is a molecule of sodium chloride NaCl? No. A molecule of sodium chloride is not NaCl. Then maybe is a molecule of sodium chloride Na2Cl2? No. Actually, let's take a look at sodium chloride. Just briefly. Here. This must be a molecule of sodium chloride here. This is a molecule of sodium chloride. How many sodiums do I have? 1, 2, 3, 4, 5, 6, 7, 8. 8 times, let's see, 1, 2, 3, 4, maybe 8 times 4. 32 sodiums. 32 sodiums and 32 chlorides. So a molecule of sodium chloride is Na32, Cl32. So that's a molecule of sodium chloride right there. Is that right? No, because you know what? I saw a smaller one than this. I saw a smaller one than that. It's got to be that. So I just saw it here. Yeah. This is a smaller molecule of sodium chloride. If I count the sodiums here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 14. So I have 14 sodiums, and that means I'm going to have 14 chlorides. 14 sodiums, 14. This is a molecule of sodium chloride. Is that right? Let's see.
if I can find something even bigger or smaller. Ooh, that's big. Sure. That's a pretty big one too. This, yeah, this is the biggest one. So should I pick the biggest one or should I pick the smallest one? Which one is a molecule of sodium chloride? There's no molecule of sodium chloride, you know, there's just, there's no beginning, there's no end. So what's the smallest unit I can have? Just pick one purple and one green, then get rid of all the rest, that's the smallest unit I could have, but is it discrete? You know, what I mean by discrete is this purple and this green paired, or is it this purple and this green? Or is it this purple and this green? Which purple and green are paired? Is it discrete that way? It's not discrete, right? So what I could have done is I could eliminate all those and call that my molecule. Or I could have eliminated all these and call this my molecule. It's not discrete, therefore it's not a unit. And so what did we call this structure? A lattice structure. So for lattice structures, do we use the molecular formula or do we use the formula unit or the empirical formula? There we have to go back because I didn't emphasize empirical formula again. You have to go back to the first week for that one. So empirical formulas are the simplest whole number ratio. And so the simplest whole number ratio, that's the same for this. So what's the simplest whole number ratio for this? NaCl. What's the simplest? NaCl. And so what these are the different sized crystals. Can you have like little tiny salt crystals and big salt crystals? You can have any size you want because there's no real beginning, no real end. And, this depends on how you grow them. And so for something, that's all we have is the empirical formula. Is this an empirical formula here? C4H10? No. Maybe C4H10 is the same thing. You know? Isn't it? Maybe we could have different sides. So for example, what is the empirical formula for C4H10? C2H5. C2H5. You're right, it's C2H5, so that's not hard. But this is different because this does not form an ionic lattice, nor does this form a covalent lattice. What this forms is molecules. How I know is because this is binary molecular compound, and we have rules for that. How would you name this as binary molecular compound? Tetracarbon decahydride. Yeah, decahydride. And so that would be the name for this, but what would the name for this one be? This one would be called dicarbon pentahydride. Now I ask you, what is the molecule? If the molecule is discrete, you know, that means it does have a beginning, it does have an end. It's a discrete unit. Well, is this a molecule of the stuff or is this a molecule of the stuff? Which one is a molecule? And it turns out this is the molecule of the stuff. And so what I have to do to get the empirical formula is I have to just break it in half, cut it in half, and that would be it. And so that's not really the molecular formula. That's not what a molecule looks like. So for example, if I had hydrogen peroxide, a molecule of hydrogen peroxide has 2 oxygens and 2 hydrogens, but something like that. However, the empirical formula for this would be HO. And so what I have to do is I have to cut the molecule in half. If I cut the molecule in half, is it still hydrogen peroxide? No. And so which one's more informative, the molecular formula or the empirical formula? If we have molecules, then we want the molecular formula. Because if I'm given the empirical formula, I don't know how big the molecule is. Now, we have different nomenclature rules. The nomenclature rules I talked to you about are the nomenclature rules for binary molecular compounds. This is a binary molecular compound, but this binary molecular compound has a different set of nomenclature rules that are associated with it. and that are preferred. This binary compound falls into the class of chemicals called what are they called? Hydro for hydrogen. Hydrocarbons. This falls into hydro. And when we name hydrocarbons, we don't follow the rules that we just learned for binary molecular compounds, even though it is a binary molecular compound. You know what we call it? We use a different set of rules. The different set of rules depends on the number of carbons in the molecule. If there are only 2 carbons in the molecule, do you know what prefix we use, or what base? It's called the base, the parent. When we have 2 carbons, do you know what we call it? We call it F. F, like ethane. If we have, or ethanol, or ethanoic acid, all those have 2 carbons. If we have 3 carbons, we call it prop. If we have 4 carbons, we call it but. And so this is actually butane. The molecule is butane, and the formula for butane is C4H10 because it has got 4 carbons. This is not butane. You know, we don't know what this is because this is empirical formula. Empirical formula is just simplified to the simplest whole number. This could be, maybe this is ethane, or maybe it's butane, or maybe it's 6. What's 6? That's right, 3. Let's do 3. Maybe it's this. What would this be? Or maybe it's, let's do 4 times that would be 8. 4 times 5 is this. Maybe it's something like this. Because all these would simplify to a 2 to 5 ratio, right? And so, if I have an empirical formula like that, we don't know if it's butane or hex or oct or dec. We don't know. And so, for molecular compounds, it's much preferred to know the molecular formula, not the empirical formula. And then we know what the molecule consists of because the molecular formula tells us the formula for the molecule itself, like hydrogen peroxide, versus the empirical formula. So if we have a lattice structure like this, you know, for lattice structure, we just try to break it down into the simplest. And so it could be a bigger crystal, it could be a smaller crystal. We just look at the simplest ratio NaCl. The same thing with covalent lattices. Covalent lattices, we just look for the simplest ratio. You know. But for molecular compounds, we want to know what, not the simplest ratio, we want to know what the actual molecule is. It might be the simplest ratio, like in water. For water, the molecular formula and the empirical formula are the same thing. Because the molecular formula, H2O, is the simplest whole number ratio, which would be the empirical formula. And so the molecular formula is going to be much more informative. However, if I have an unknown substance like this, you know, let's take this. First thing we want to do is we want to know if it's a mixture or pure. If it's a mixture, we want to separate into its pure components. And so let's say I have a pure compound here, not an element, because there aren't that many liquid elements. Do you know what liquid elements there are on the periodic table? There are only 2 that are liquid. Hydrogen is a gas. Nitrogen is a gas. Mercury. Mercury's 1. Is this mercury? No. And the other would be bromine. What would be bromine? The others are solids or gases. And so this is not an element. And if it's pure, then that means it's got to be a compound. And so what is the formula for this compound? That's what I want to know. And so what I got to do is I got to do a process called chemical analysis. Did I talk to you about chemical analysis? No? There are lots of expensive machines you can use to analyze unknowns, to figure out their composition, elemental composition. So one of the machines they sent to the moon and they sent to Mars, I think. And that machine blasts X-rays on samples and then see what kinds of light come off. It's called X-ray fluorescence. So you get a fluorescence of X-rays coming off that, and from that you can figure out the elemental composition. But there are lots of other techniques we can use. And so that's somewhat specialized. So normally what you would probably do is you'd probably take a sample of this and send it out for analysis. You want to send it out for analysis and see what they say. I've done the exact same thing. I've had some unknown samples I've sent out for analysis, and they check it. But when they send back the data, they don't send you back the formula of the. You know what they send you back? The percent composition. Do they send you the percent composition by atom or the percent composition by mass? They'll send you the percent composition by mass. Sometimes they don't even send you that. Sometimes you send them a sample, they'll weigh it, and they'll say this many grams of this many grams of that. That's it. And from that you can get the percent composition. Well, if we have the percent composition, then all we can hope for is an empirical formula. And so sometimes we can't avoid it, and we just have to get the empirical formula. So let's take a look at this here. We sent out a sample. They did some chemical analysis. It's a pure compound. If we do a mixture, then it would just be kind of weird. You know, how many grams of carbon in your laundry detergent? You're probably more interested in how many grams of phosphate in your laundry detergent. So a sample of pure compound is made up of 1.61 grams of phosphorus, 1.61 grams of phosphorus and 2.98 grams of fluorine. 2.98 grams of fluorine. How many total grams do we have? 7. No, sorry. 1 and 8 is 9. 4. 4.59 grams of sample. That's assuming there are only 2 components in the sample, phosphorus and fluorine. Oh, did I get this right? Is it F or F2? F2. It's F2? So if I have a sample like this, it consists of phosphorus and fluorine, F2. Well, sometimes you can see visually. You know what fluorine looks like? Let me show you what fluorine looks like. This is what fluorine looks like. It's a yellow-green gas. Kind of like chlorine, right? You'd expect it because it's in the same family as chlorine. So maybe we have some white or red phosphorus and some yellow-green fluorine gas in this compound. Is that right? That's like, oh, I know, water. Water consists of hydrogen gas. Hydrogen gas is a clear, colorless gas, and half an oxygen gas. I don't know what half an oxygen gas looks like, but it probably looks like regular O2. It's not as happy of a version. Is that what water is made of? Hydrogen gas? And half an oxygen gas? No. And so when they say fluorine, are they talking about F2, which is this green gas, or are they talking about atoms of fluorine? They're talking about atoms of fluorine. And you know, what that means is if there are only 2, it could be like something like PF, or maybe it's like PF2, right? Or maybe it's something like PF3, maybe PF4, PF5, PF6, PF7, maybe it's P2F, P2F2. Well, P2F2, use kind of similar to, yeah, look at the empirical formula. Let's cancel that. Maybe it's P2F3. How about that? Etc. And so all these just have different numbers of fluorine atoms. Just because I have 2 fluorine atoms doesn't mean it's green gas, right? Mixed in with white phosphorus. It's just 2 fluorine atoms bonded. So here, if you started looking for hydrogen gas, you're never going to find it because the 2 hydrogens are separated. In fact, the 2 hydrogens are not even bonded to each other. The 2 hydrogens are linked to the oxygen. It's not hydrogen. Hydrogen is 2 hydrogens linked together like that to form gas. The 2 atoms put together. And so, you know, this, yeah, it could be like something like PF2 like that, but, you know, I wouldn't think it's this. I don't know how many fluorines there are. Do you? No, we don't. But this is why we send it out for chemical analysis, so we can figure out how many fluorines there are. If you send out the sample for chemical analysis, let me ask you this. Let's this will be like a little mini quiz topic here. The mini quiz. Let's pick this one, PF6. Should we even consider PF6? Is PF6 a possibility? Or should we eliminate it? Should we eliminate PF6 as a possible formula for the unknown? How about PF5? No, do not eliminate PF5 because you know PF5 exists. PF5 exists. Well, heck, if PF5 exists, then PF6 must exist, right? Okay, so tell me, well, if you think no, I see his head shaking no, then why? Why or why not? Why or why not? That will be the mini quiz. This will be open book, open notes, and then you can consult with your friends and neighbors if you want. So.